Good morning, students. So we are continuing with the continuous time Markov chain. So let me just share. I think my screen is visible. So last time we started with the continuous time Markov chain. So as last time also I explained that some student was asking j can also because no value it is not specified that I is not equal to just I j can also take I PIIT is also possible. Okay. So U is basically, this is continuous time. So U is continuous, okay, here, and xt can take discrete values. Okay, so that is non-negative integers. Also, one question was asked about this, that sojourn time, the amount of time stays in state type before making a transition to different state. Then using star, using the Markovian property, we get that Ti greater than S plus T given Ti greater than S is probability Ti greater than T. So then Ti is exponential and Ti is exponential, then this also implies this. So this question was asked. So that proofs was rigorous. So I have told to give you the proof today. So you can go through that. I have written here question asked in the class. So this is the question that t greater than t, given t is greater than t is probability t greater than x. So let us assume that t has CDF g. Then we have to show that g bar x plus t, where g bar is the reliability function, is g bar t, g bar x. If and only if g bar x is e to the power minus lambda x, that means exponential. So using the exponential distribution has no memory property. So therefore g bar x will satisfy probability t greater than x plus t given t greater than t and probability t greater than x. Now conversely, that means when no aging properties, then this is exponential. So that proof you can just see. I have given the detailed proof here. So detailed proof is given here. So that involves much rigor. That question was asked. That involved much rigor. So you can go through that. I have done the proof of that. Okay. So now, yes. So is it okay?
Yes, sir.
Okay. So this you can just go through that. Some student was asked this question, so it involved much rigor. So you can just go through that. I have each and every step I have explained here. Now we are doing the basically some examples of we have continuous time Markov chain, particularly in birth and death process. We are particular birth and death process we have seen. When there are n people in the system, the new arrival enter the system at an exponential rate, and people leave the system at an exponential rate. So then lambda n is the arrival rate and mu n is the departure rate. Then v naught is lambda naught, vn is lambda n plus mu n, and pn to n plus 1 lambda n upon lambda n plus mu n. Okay, where okay. So now let us take another example. So M1 queuing system. So inter-arrival time, first M means that Markovian, that means inter-arrival times are exponential with the parameter lambda. Second M is service time distribution is exponential with the parameter mu, and one server is there. So for example, one server is there and the arrival pattern is basically the Poisson process. That means the inter-arrival time distributions are exponential and service is provided according to the exponential distribution. So this is clearly birth and death process because the inter-arrival times and exponential, service time is also exponential. So therefore clearly birth and death process with lambda n is lambda and mu n is mu. So here the xt denotes the number of customers in queuing system at time t. So number of customer can be 0, 1, 2, so on. So arrival rate is lambda, departure rate is mu. So that means we can say here lambda naught is lambda, lambda 1 is lambda, mu 1 is mu, mu 2 is mu, so on. So this is the MM1 queuing system. So similarly, we may have, instead of one server, S servers are there. So then that is called the multi-server exponential queuing system. Or MMS queuing system. So first M denotes that inter-arrival times are exponential with the rate lambda. Second M denotes that service time distribution is exponential with parameter mu, and S servers are there. Same as previous one, but here servers are S in numbers. So this is also a birth and death process because the inter-arrival times are exponential and service time distribution is exponential with parameter mu. So there are, let us say, 0 customer, 1 customer, 2 customer, S minus 1 customer, S customer, S plus 1 customer, S plus 2 customers, so on. So if 0 customers are there, then customer can come according to the rate lambda. And if there is one customer and S servers are there, okay, then only one customer will be in one server. So therefore rate is mu from 1 to 0. If there are S servers and 2 customers are there, then 2 to 1. Then minimum of, let us say, y1 is giving, y1 is the first server, y2 is the second server, and ys is the server. Okay, so these two servers are busy because 2 customers are there. So when from 2 to 1 we will go, whenever minimum of y1 comma y2, whenever one of them will give the service first. So minimum, because y1 is exponential with parameter mu, y2 is exponential with parameter mu, minimum of y1 y2 last time as we have shown is exponential 2 mu. This rate is 2 mu here. Similarly, here rate is S mu. Here rate is, but note down here that S servers are there. Since S servers are there, so therefore S servers are busy and one customer is in line. So rate will be S mu and rate will be S mu. So therefore, this is a birth and death process with the lambda n is equal to lambda, n is 0, 1, 2 and so on, and mu n is n mu, n is 1, 2, so on to S, and this is S mu when n is S plus 1, S plus 2 and so on. Okay, so this is the birth and death rates, that means the arrival and departure rates. So any question in this multi-server exponential queuing system? Okay, so am I audible?
Yes.
Yes, sir. Can you
Okay, okay.
explain once?
Yes, yes, yes. So here multi-server exponential queuing system. So we have, let us say, S servers are there, 2 S servers are there, and let us say programs are coming to get processed here in these servers. So if, because there can be 0 programs, 1 program, 2 program, and so on. Many programs are 0, 1, 2, 3, and so on. Okay. If one program is coming, so it will go to the server and get processed. But at what rate? Because server, these are coming according to rate lambda, exponential with rate lambda, inter-arrival times are exponential lambda. Inter-arrival time for coming of the programs is exponential lambda, or that means they are coming according to the Poisson process with the rate lambda. So rate is basically remains lambda. Rate remains lambda, lambda, lambda. But when one there is one program is there, so that will be processed with rate mu. Okay, when there are 2 programs there, okay, then when there remains 1 program, when any of them will get processed, and what is the distribution of that? Because programs are processed in the server according to exponential with parameter mu. Okay, so what is this? First, one of them will get processed. That means minimum of y1 comma y2, where y1 is that it is processed in the server one according to the exponential distribution. And because these are exponential with parameter mu, both of them, so minimum will be exponential 2 mu. So therefore, this is 2 mu. Now, similarly, if S up to S, this remains S mu, 2 mu, 3 mu, S mu, and when it becomes S plus 1, so then S will be there and 1 will be waiting. Okay, then how do we can move to S, because that will also remain S mu because servers are S. Is it okay?
Yes, sir.
Okay, now let us do the expected time to go from state I to state J in birth and death process. So we have a birth and death process. That means the arrivals are according to the Poisson process. That means inter-arrival times are exponentially parameter mu n if there are n customer, and service is provided according to the exponential distribution with parameter mu n. Okay, with birth rate, lambda n, and death rate or departure rate mu n. N is from 1 to infinity. So 0, 1, 2, so on. This is lambda naught, lambda 1, mu 1, mu 2. This is the state transition diagram. Let Ti is the time starting from state I. It takes for the process to enter state I plus 1. So Ti is the time starting from state I it takes for the process to enter I plus 1. So this is Ti is different from the previous Ti. So maybe you can denote this by Ti star. Okay. So to make it different from previous Ti, that was the sojourn time. Ti is the time starting from I, it takes for the process to enter I plus 1. Okay, then T naught. T naught is basically starting from state I, it takes the process to enter state I plus 1. So that is basically nothing but sojourn time. So this is exponential with parameter lambda naught. So therefore, this is expected value of T naught with the rate 1 by lambda naught. Okay. So now let for I greater than 0, let I is 1 if the first transition is from I to I plus 1. Kindly mute yourself. If question is there, then you ask. If the first transition is from I to I minus 1. Let us denote a counter which counts if the first transition is from I to I plus 1. 0 if I is from I minus 1. Then what is expected value of T I star given I is equal to 1? That means starting from state I, we are entering state I plus 1, given that first transition is from I to I plus 1. But we know that since independent of whether the first transition is a birth or death, the time it occurs is exponential with rate lambda I plus mu I. So you know that in birth and death process, so we can move outside with exponential rate with the parameter lambda I plus mu I. Since time either a birth or death occurs is exponential with the rate lambda I plus mu I if we are in a state I. So therefore, that is exponential. So therefore, expectation of that will be 1 divided by lambda I plus mu I. Why? Since independent of whether the first transition is from a birth or death, the time it occurs is exponential with the rate lambda I plus mu I. Okay. So it's independent of whether the first transition is from birth and death, because either we can move from I to I plus 1 or I minus 1 in birth and death process. So we are moving minimum of x comma y, where x is exponential with rate lambda I, y is exponential with rate mu I. So minimum of x comma y will be exponential with rate lambda I plus mu I. So therefore, mean of that will be 1 divided by lambda I plus mu I. And clearly, we are moving from I to I plus 1. So therefore, this is the rate. Now, what is the expected value of Ti star given I is equal to 0? That means we are finding the expectation average of starting from state I, it takes the process to enter state I plus 1, given that the first transition is from I to I minus 1. But we know that whether independent of whether the transition is birth or death, rate is lambda I plus mu I, therefore mean will be 1 divided by lambda I plus mu I. And but we know that we have moved backward. That means now we are in I minus 1. First of all, we have to move to I plus 1. Then from I plus we have to move from I minus 1 to I, that is Ti minus 1. And then from Ti, we have to, from I, we have to move to I plus 1. Mean of that is expected value of Ti. Because Ti is the, starting from I, it takes the process to enter I plus 1. So Ti minus 1, starting from I minus 1, it takes the process to enter I. Okay, so this is the value. Okay, so now, is it clear? Now, expected value of Ti is expected value of Ti star given I. Okay, so therefore inside is a function of some phi I. So expectation of that, that means this is equal to expected value of Ti star given I is equal to 1 into probability I is equal to 1 plus expected value of Ti star given I is equal to 0 into probability I is equal to 0. So this is also known as the, using the law of total probability, law of total expectation. Okay, so in this fashion you can find out. Now both the values are with you. Expected value of Ti given I is equal to 1. This is 1 divided by lambda I plus mu I into probability I is equal to 1. I is equal to 1 means first transition from I to I plus 1. Can anyone tell what is the value of probability I is equal to 1 in birth and death process? We are moving from state I to I plus 1. We have already done this. That means probability that birth occur before a death. So can anyone remember what is the value of that? Birth occur before that in the birth and death process. Probability birth occur before a death. So this is lambda n upon lambda n plus mu n. That means in this case lambda I upon lambda I plus mu I. Okay, so this is the value. So therefore this value is lambda I upon lambda I plus mu I plus this value is 1 divided by lambda I plus mu I plus expected value of T star I minus 1 plus expected value of Ti star. And what is the probability I is equal to 0? Death occur before birth.
Mu n by lambda n plus mu n.
Yes, yes. So in this case, because state I we are taking, so mu I upon lambda I plus mu I. So after solving this, we will easily find out the answer that this implies that because this expectation is on both sides. So expected value of Ti star is 1 divided by lambda I plus mu I upon lambda I. Expected value of Ti minus 1 for I is greater than equal to 1 and expected value of T naught is 1 divided by lambda naught. So what is this is the expected time from going from I to I plus 1 in the birth and death process. Okay, now therefore expected time to go from I to state I to state j, where I is less than j. So this is from, first of all, we have to go from I to I plus 1, then from I plus 1 to I plus 2, then from j minus 1 to j. So this is the expected time from going from state I to state j in the birth and death process. Okay, so this was about the birth and death process. So now let us continue with the our continuous time Markov chain in general. So for any pair of states, so I and j are states. So let vi, we are denoting the rate at which the process makes a transition when in state I, and Pij is the probability that this transition is into state j when we are in state rate when we are in rate state I, probability that it make a transition into state j. Next it make a transition into state j, that is probability is Pij, and Qij is the rate when in state I at which the process makes a transition into state j. So note that Qij is Vi into Pij, because Qij is the rate when in state I at which we make a process make a transition into state j. So this is the rate with which we are in state I into the probability with which we are moving out from state I to state j. Okay, and summation from here, summation j Qij is Vi summation j Pij, but we know that sum of the probability is 1. So therefore this is Vi. Now we have uh, some lemmas. Let us do some lemmas. Limit h goes to 0, 1 minus Piih upon h is Vi or basically we are denoting vi. Okay, so now, and okay, so second is limit as h goes to 0, pij h upon h is qij when I is not equal to j. So solution is, note that one minus piih. That means in when we are in state I, in small h time, we are in not in state I, we are moving outside. So because in the continuous time Markov chain, we know that sojourn times are exponential with parameter vi. Okay, so sojourn time is the amount of time spent in that state. So that will be, because exponential distribution has relationship with the Poisson process, so that will be vih plus small oh. Okay, using the definition of the Poisson process also. So therefore, taking limit as h goes to 0, 1 minus piih upon h. So this is vi, h will cancel out, plus oh upon h, as limit as h goes to 0 by definition of small oh function, that will be 0. So therefore, this is the first proof of the first part of lemma. Second is, note that pij h. So pijh basically rate with which we are moving from I to j into h plus small oh, because horizontal times are exponential. Now in the same fashion, limit h goes to 0, pih upon h is qij. Okay, so this is the proof of that. Now let us say this is our lemma star, and now let us do the, let us say lemma a, just a name. Okay, for all s greater than equal to 0 and t greater than equal to 0, pij t plus s is summation k is from 0 to infinity, pikt pkjs. This is known as the Chapman-Kolmogorov equations. In continuous time Markov chain. So let us see this Chapman-Kolmogorov equations, the proof of that. So Eij t plus s. By definition, this is the transition probability x t plus s is equal to j, given x naught is equal to I. Now this is summing over k probability x t plus s is equal to j, xt is equal to k, given x naught is equal to I using theorem of total probability. Okay, now applying the definition of conditional probability, probability of A intersection B given C is probability of A given B intersection C into probability of B given C. So K is from 0 to infinity. Probability X T plus S is equal to J given xt is equal to K, x naught is equal to I into probability xt is equal to K given x naught is equal to I. Okay, now because it is a continuous time Markov chain, it will forget the past. So therefore this is summation K is from 0 to infinity probability x T plus S is equal to J given xt is equal to K to probability xt is equal to K into x not equal to I. This is summation K is from 0 to infinity P state K to J in S because of the stationary tension probability T to T plus S, that means time gap is S, into P tension probability from I to K in T time. So that is the answer basically. So this was we want to show that Pijt is summation K is from 0 to infinity Pikt Pkjs. This is the Chapman-Kolmogorov equations. So any question till now? Okay, am I audible to you?
You are audible, sir.
Okay. Okay, now let us move further. Okay, so next is known as the Kolmogorov backward equation. So for all states I and j and states I and j and time t Pij prime t, that means derivative of this is summation K is not equal to I Q Ik, that is the rate with which we are moving from I to K, Pkj T, that is the transition probability, minus Vi Pij T. Let us see the solution of this. So Pij H plus T minus Pij T. So now using CK equation, Chapman-Kolmogorov equation, this can clearly be written as summation K is from 0 to infinity Pikh Pkjt, okay, minus Pij T using Chapman-Kolmogorov equations. Now take out the ith term from here and plug in the other Pikh Pkjt minus Now we are ith term is pik h pijt. So 1 minus piih pijt, because ith term we are taking out from the first expression. Now therefore take limit as h goes to 0, pij t plus h minus pijt upon h, which is because we are dividing by h here, taking the limit. So we will have limit h goes to 0, summation k is not equal to I, pik h upon h pkjt minus 1 minus piih upon h pijt. Okay, therefore this implies that pij prime t is summation k is not equal to I, and take limit of this using the lemma star. Using lemma star, you know that this is the second term qij, and the first term is vi. Pijh upon h is qi, limit of that is qij. So therefore this value is, limit of that is qik pkjt minus, now take the limit of this, this will be vi by the lemma star a part pijt. So this is using lemma star. Okay, so this is the value. Now let us find out the, take an example of find out the Kolmogorov backward equation for birth and death process. So we know that from the birth and death process that for birth and death process, V naught is lambda naught and Vi is lambda I plus mu I, the parameter. P01 is 1, Pi2I plus 1 is lambda I upon lambda I plus mu I, and Pi2I minus 1 is mu I upon lambda I plus mu I. Also, we know that Qij is Vi into Pij. So therefore, Qi to I plus 1. This is Vi into Pi plus 1. So this will be lambda I. That will be lambda I from here. And Qi to I minus 1. This will be Vi into Pi minus 1. That will be lambda I plus mu I will cancel out. That will be mu I. And Qij is 0 if j is not equal to I minus 1 and I plus 1. So that is the value. So this is the backward equation for birth and now we are finding the backward equation. So let us say we are denoting this equation by, this is the backward equation, 1 star, okay, 1 dash. So from 1 dash, what is Pij prime t is now qi2, if q is not equal to I and I minus 1 and I plus 1, that is 0. And if it is, let us say, I plus 1, then this is qi to I plus 1, that is lambda I, and pi plus 1 to j plus, if k is I minus 1, qi to I minus 1 is mu I into p of I minus 1 to j t minus vi pijt. Vi is in the birth and death process lambda I plus mu I. Pijt Pijt. So where I is greater than 0. So also P0 j dash t, P0 j dash t, okay, for, so that is q I 1, that is 1, because we are taking I as 0. Okay, so Q01, Q01 is uh, lambda naught, and P1 JT, and Vi in that case is when V naught is lambda naught minus lambda naught, and P0 JT. Okay, so using this backward equation, we have find it out these two equations for birth and death process. So we can solve these equations and find out the answer for PIJT for birth and death process. Okay, so any question till now?